is including, let me start here, okay? Inspiratory reserve volume. It's when you force air in and as much as you can. That's all you can breathe in, okay? Another easy one, expiratory reserve volume. When you blow everything out, there's nothing left to blow out. That's your expiratory reserve volume. Now, tidal volume is the one that you breathe normally, quietly, okay? Now, even after you, let's say you blow everything out, okay, you will still have something called a residual volume. Okay, why? Because in the alveoli, remember, it keeps its shape. It doesn't completely collapse. So that's what stays in there. Okay? This is called a residual volume. So again, inspiratory reserve, breathe in as much as you can. Expiratory is blow out as much as you can. And this is normal breathing. And this is leftover. Okay? Leftover. Okay? Inspiratory capacity is just another term for how much you can actually breathe in. So you breathe in your regular ones plus your forced breathing. Okay? And this is called functional residual. And vital capacity. Okay? Vital capacity is life, whatever you need for life. Okay? And this is the total lung capacity. Total lung capacity include all these terms, okay? Include all these. And one of the things to measure breathing is called a spirometry. Again, here are some more terms if you want to look into it, okay? But, yeah. Oh. Something to look into is called the anatomical dead space. That is air in the conducting passageway that's not being exchanged. So when you breathe in the air, for example, in the trachea or in the bronchi, there's no alveoli in there. Okay, so air comes in and go out, and they don't actually get exchanged. That's called anatomical dead space. Alveolar dead space, air in the alveolar that is not being exchanged. Okay. For example, when you have a disease like COPD or whatever in the lungs, okay, total dead space is called is both of these together. Okay. Respiratory rate and control ventilation rate of number of breathing per minute, whatever it needs your need. So you have the respiratory center in the medulla. Okay. That's why, again, sometimes if you get hit in the back of the neck where the medulla is, you may not be able to breathe and you could die. Okay. Medulla sets the basic rhythm for breathing. Normal breathing is rhythmical and involuntary. And remember, one of the reasons we breathe is for ATP, as well as the buildup of carbon dioxide. Okay, and there's respiratory respiratory chemoreceptors called chemoreceptors that can detect carbon dioxide, oxygen level, and your pH level, because your breathing can also affect your pH, as we will see shortly. Okay, so here are some of the chemoreceptor areas we saw earlier. In the aorta, it monitors partial pressure of oxygen and CO2 and pH. Okay, so here it is in the brain, respiratory center. Okay, the pons. Okay, here is the medulla. Okay, so here are the respiratory center that will control the muscles and the lungs. If we look at this carefully, so this is the anterior portion of the medulla. Here's the posterior portion. Remember the little cerebellum here. So the dorsal respiratory group, the back, okay, it will help with normal breathing. Okay, the ventral one, which is ventral means the front, okay, the ventral one, it will help with forced inspiration and expiration as well. Oh, here it is. Dorsal, it will stimulate the diaphragm for constant breathing rhythmic. So the dorsal one in the back for normal breathing. Okay, again, normal breathing is with the diaphragm and the external intercostal. And the ventral groups, okay, with forced breathing using accessory muscles, your scalene, your SCM, and your internal intercostal. Okay. The pontine, okay, right here. Pneumotaxis inhibit dorsal root ganglia. So this will inhibit this guy. Okay. Let's see, factor affecting your rate and depth. So what makes it? What makes your breathing? Like what stimulate your breathing? Okay. The brainstem, but it also needs input from the body. You remember we have chemoreceptor. Okay, we saw them there, you know, in the aorta and things like that. It can read partial pressure. Okay, carbon dioxide in the arterial blood and the CSF. CSF, you'll have concentration of hydrogen ion. Okay, which means pH. In the arteriole, there's concentration of the hydrogen ion, okay, due to the metabolic process. And partial pressure of oxygen, which needs to be low. The chemoreceptor only senses dissolved oxygen. How do you sense the breathing? How do senses affect the breathing? So as you remember, whenever there's an increase of CO2, okay, whenever there's an increase of CO2, there's also an increase in hydrogen ion, okay? Then when these two increases, so CO2 increase hydrogen ion means the pH goes downward, you become more acidic. So concentration of CO2 and the decrease of pH will stimulate the central chemoreceptor. Okay, that's the CSF. In the blood, same thing. In the blood, there's an increase of CO2, hydrogen ion increase, which means a decrease of pH, or the oxygen stimulate the peripheral chemoreceptor. Okay, so CSF, you know, is in the brain, okay, and the spinal cord. So that would be the central chemoreceptor, and anywhere else would be the peripheral chemoreceptor. And you also have them in your carotid, and then you in your aortic arch. Okay. So when this increase, okay, you breathe out more. Okay. And when there is too little, you will have less breathing, depending on what the body needs. Part 2, gas exchange. So these are some of the gases we have on in the atmosphere. Remember we saw Boyle's law earlier. Okay. In the air, okay, is mostly nitrogen, oxygen, okay, there's some water, carbon dioxide, okay. Gases are independent of each other, okay. This is called Dalton law. They will exert their own pressure. Here's the pressure of the oxygen, here's the pressure of nitrogen, and here's the pressure of oxygen and nitrogen, and then you combine them together. See, they have their own pressure, okay. That's called Dalton law. By the time air passes through the conducting division, gases mix, and therefore by the alveoli, this is what you have. How do you get them in the blood? A liquid. Okay. How do you get the gas into a liquid? Okay, here's where the Henry's law comes in. This is when gas can be dissolved into a liquid. Okay, so dissolving gas. So this depends on how hard you push. Okay, and the solubility of the gas. This is called Henry's law. So again, depending on how soluble the gas is, that's when it is get exchanged into your blood. So then, when it gets to your blood, it goes through simple diffusion. Do you remember the alveoli is? So here's the alveoli. Okay, here's the blood. Okay. Surface area, partial pressure difference, solubility of gas, and distance or thickness of the membrane. Okay. So of course, the partial pressure. Okay. Again, it is. So here's the alveoli. Okay. Partial pressure of the. Let's start with CO2. So what do you think it's going to be? CO2. You think CO2 is going to be high here or low here? Okay. Of course, it's going to be high here, so that it can be diffused across. Remember we talked about diffusion. Whenever there's someone with a strong perfume comes in, it will diffuse. Okay, so very strong here, and then it will diffuse across here. What about oxygen? It will be on opposite, right? Oxygen will be high concentration here, and then it will now diffuse to the low concentration. Okay, low concentration of the blood here. So once everything is exchanged, this is now filled with oxygen, very little carbon dioxide left. And then now these are oxygenated blood. Okay. Before all the exchange, this is the deoxygenated blood. Again, it has to go through a very thin membrane, just one layer thick, remember? Okay. Simple summary. Diffusion through respiratory membrane. External respiration, oxygen in, carbon dioxide out. So this is the external part. As the oxygenated blood reaches the alveoli, low partial pressure of oxygen. So here in the capillary, there's low oxygen, okay? And because it is high in the alveoli, so oxygen in, okay? Oxygen in here, and then it will bind to the